In Module 7, we're going to look at sensitivity analysis and how can we reuse some of the tools we've seen in Module 6 with form analysis. So a little recap is X is our vector of random variable involved either in the solicitation or in the resistance. F of X is their joint probability density function. G of X is our limit state function, which is going to be positive in the survival domain, negative in the failure domain. G of X equals 0 is my limit state surface. The boundary between my failure and my survival domain would define omega, omega being my failure domain here. So the problem we're trying to solve in module 7 is what if using what we've seen in the previous module, using either Monte Carlo analysis, form, SORM, MCF/OSM, we compute a reliability index or a failure probability that don't satisfy requirements. Okay, so say our beta is too low compared to what is specified in the construction code. Then I need to take the current beta estimate and I need to intervene on the structure by either putting reinforcement in place or by gathering information to reduce some of the uncertainty associated with my random variable. But the first question is, what is the relative importance of each of my random variable to know on which one should I act upon? Okay, so what is the relative importance of each of those ith variable into the failure probability and my reliability index beta? And this is also what's going to affect the code calibration. So when we have uh, load resistance factor design, where we have coefficients that will weight up the the loading and weight down the resistance when I design or analyze structures, how do I calibrate these factors that will weight up or down each of my variable? And this is based upon the same relative importance of my variable. We're going to see this. Second, how can we compute the sensitivity of my failure probability and reliability index with respect to the parameters involved in my joint probability density? So we want to quantify the importance of those parameters on that reliability. And finally, some of these parameter theta that are involved in the reliability computations or in the definition of my joint PDF are fairly hard to interpret. In the case of a Gaussian, it's easy, it's a mean invariance, but for other probability density, it might not be as easy to interpret. So how can we transform everything so we have our sensitivity with respect to the mean and standard deviation rather than the native parameters that we can have for other probability densities? And all of these, we're going to see we can build upon the form approximation that we've seen in module 6, and we can reuse these, especially the alpha vector, the normalized negative gradient vector alpha hat can be reused to compute those sensitivity analysis. So introduction, this is what we've just covered. We're going to see first that we need to reorganize our limit state function into this form in order to express the sensitivity of each random variable. This is the first thing we're going to see. Then we're going to see how can we reuse this form in order to measure the importance of each random variable into Z, normalized safety margin. Then we're going to see how can we calibrate the coefficient involved in the load resistance factor design. So how can we use the reliability concept we've seen so far to do this calibration? Then we're going to look at the importance of random variable into the reliability and how can we transform that sensitivity, not with respect to the parameters of any PDF, but only the mean and standard deviation, which are going to be more interpretable. And that brings us here, module 7. This is our first module where we're looking at the toolbox that we're going to have in order to to apply the result we've obtained in the previous module into practical context where, for instance, we don't satisfy the reliability index prescribed by the code. How do I act upon my structure or the parameter involved in my structure in order to increase that reliability index? So first, we need to reparametrize our limit state function and limit state surface. So in the standard normal space, we've seen that g of u is approximated by the first order Taylor series expansion that says that we're going to have g of u star. So u star being on the limit state surface, g of u star should be 0, plus the gradient of my limit state function, evaluate my design point u star, times u minus u star. So if we distribute that gradient into my parentheses, I'm going to get the following form. And in this case, we've seen in the previous module, 5 and 6, that my beta is defined by the ratio by the mean of that linearized limit state function divided by its standard deviation. So the mean here is simply the part that is in front of my u star, so gradient of u star. And the standard deviation is going to be the gradient times identity matrix times gradient transpose. So here, the beta is going to be equal by this quantity, where what we have on the left-hand side is the negative normalized gradient, or my alpha at, and alpha times u is going to be equal to my beta. So if on that equation here, I just have to multiply it by this ratio. So the ratio of the norm of the gradient divided by its norm, it must be 1. So I'm not going to change my equation by doing so. But if I distribute this ratio inside here, I can see that I'm going to recognize that the gradient divided by its norm negative, this is going to be alpha. Minus alpha times u, that's going to give me beta. If I divide here, it's going to be gradient divided by its norm. This is going to be minus alpha. So I'm going to have the gradient times beta minus alpha u. Okay, so I've simply reparametrized that limit state function in terms of beta and alpha. So in that case, we can see that the probability of failure is the probability that beta minus alpha u is lesser or equal than 0. Just like before, PF was probability that g of u lesser than 0. That g of u less than 0. No, less than minus beta. So g of x less than 0. Anyway, so here we have our limit state surface. So in sine, we have beta minus alpha u equals 0 here. And we can see if I'm directly on the limit state surface. So I'm at u star. In this case, alpha times u star is going to give me my beta. We still have alpha hat here, which is my negative gradient vector. And if I place a point here, so I'm at a point u, if I do alpha times this coordinate u, so the product of these two vectors is going to give me a scalar, which is here a length that is, in this case, smaller than beta. So beta minus alpha u is going to be greater than 0. I'm going to be in my survival domain. On the opposite, if I take this point and I do alpha times u, is going to give me this scalar, and this scalar is greater than beta. So beta minus something greater than beta, I'm going to be in my failure domain. So we can see how this reparametrization is still a valid limit state function that gives us exactly the same objective as what we had before. So now we're going to reuse that new parameterization in order to quantify the relative importance of each of my random variable into a normalized safety margin. So first, we're going to see a little recall of those safety margin. We're going to see how can we do such sensitivity analysis for independent random variable. Then we're going to see how our alpha i's are these sensitivity analysis. We're going to apply it. We're going to extend it to a case where our random variables are not independent. And that's going to lead to a new sensitivity matrix, which is going to be our gamma hat. And we're going to also apply it to an example. So little recap about the safety margin. So imagine we explicitly have R and S, two random variable quantifying the resistance and solicitation. We're going to define Z being a safety margin, meaning the distance between R and S, so R minus S. So Z less than or equal to 0 is my failure, where probability of failure is simply the probability that this event happened, that safety margin is less or equal to 0. So when my random variable are independent, so we have our limit state functions such as this, z equal g of x equal g of u. So g of x or g of u are equivalent to my safety margin, which is just a special case of it. So in that case, what we've done before is that we're going to linearize that limit state function, or we're going to linearize that safety margin by saying as we formulate in the previous section. We're going to have the norm of the gradient of my linearized limit state function times beta minus alpha u. So here, if I send that gradient on the left-hand side, I can have a normalized a safety margin. So z divided by the gradient of the norm of my gradient, which is simply just a scalar. So in that case, we can say this is approximately equal to beta minus alpha u. So if we expand alpha times u, it's really alpha 1 u1 plus alpha 2 u2, etc. So in that case, if we want to compute what is going to be the expectation of the term here on the left-hand side, the normalized safety margin, since this is a linear function, so the mean of that linear function is going to be a constant term plus the mean of all these terms is 0. So this is going to end up being 0. So if we have y equal ax plus b, I'm going to do a times mx plus b, where in this case, the only term remaining for mean is going to be beta. For the variance, what I'm going to do, so beta is not involved in the variance. I'm going to have alpha times a identity matrix covariance here for you. So it's going to be alpha times identity times alpha transpose. So that's going to give me the norm of my gradient vector alpha, normalized gradient vector alpha, sorry. So it's going to be alpha 1 square plus alpha 2 square up to alpha n square. And since it's the normalized vector already, this is going to give me 1. So we can see here that alpha square corresponds to the contribution of each of my ui to the variance of my normalized safety margin. And this is going to indicate that these alpha square are directly my importance measure. So if xi and xj are independent for all I not equal to j, this alpha square is my importance measure, which is going to measure what is going to be the contribution of my ith variable to the normalized safety margin. And here we can also interpret the sign of these coin, where when we have a negative value for alpha, it's a sign that the variable associated with it contributes to the capacity. If it's positive, it contributes to the demand. And how is that? It's because here we see that if we have an alpha that is negative, if we increase u, we're going to get away from in the negative domain. And the opposite, if alpha is positive, since we have the negative sign here, if I increase u, I'm going to get closer to going into my negative domain. So if we look at this in an applied example, we can see here we have our domain for u1, u2. And here, if we look at the sign of alpha 1, alpha 2, so alpha 1 is going to be negative, alpha 2 is going to be positive. So meaning that alpha 1 is related to capacity, alpha 2 to the solicitation. And since the magnitude of both alpha is roughly equal, the importance of the two variables is also going to be roughly equal. If we have another example like this, the sign is still the same, but now alpha 1 is less than alpha 2. It means that alpha 2, x2 or u2 is going to be more important than x1 into my normalized safety margin. If we have something like this, now we change the sign. We're going to say that alpha 1 is positive, alpha 2 is negative, meaning that alpha 1 now is associated with the demand, alpha 2 is associated with the capacity. And now since alpha 1 is much greater than alpha 2, it means that x1 is much more important than x2. So if we apply this to a component reliability problem, we have our bar subject to a tensile force S, which has a resistance R, where the resistance is governed by the cross section of my bar. So d squared times f of y, the elastic limit f of y, which is 300 megapascal. So in this case, d, which is going to be the dimension of my bar, is going to be log normal. X, which is the solicitation, is going to be Gumbel. These are the mean and standard deviation for each variable. So in that case, if we apply the same thing that we've seen in example 6.2 from the module where we saw form, we can see that from the alpha we've already computed, we have alpha equal to minus 0.77 and 0.64. So that indicates us that both variables have roughly the same relative importance, with the dimension being slightly more important. With respect to the sign, we have a negative sign for the first variable corresponding to d the dimension, which indeed contribute to the resistance. On the other hand, the solicitation, the tensile force applied on it, has a positive sign, which indeed correspond to the loading, a loading variable. So we can both interpret the magnitude and the sign of the quantity in our alpha vector. However, what happened now if the correlation coefficient between my variable is not zero, where we have strong dependency between x1 and x2? I cannot anymore directly use the alpha vector because it's not going to correspond. It's going to be still valid in the standard normal space, but it's not going to be valid anymore in the original space. So when my xi are dependent, what do? There's no more a direct correspondence between the alpha I square and the normalized safety margin. So what we need to do is that we need to linearize our transformation function from the original space x to the standard normal space u. And we want to linearize that transformation at the design point u star. So to do this, t of x, remember, this is my transformation function, which is typically obtained using the equality of the CDF. So in that case, we're going to linearize that equality of the CDF at u star. So that's going to give me, going from x to u, is going to be u star plus the Jacobian from u to x, the partial derivative of my transformation function, evaluated at x minus x star. I'm going to do the same thing here, where x is going to be equivalent normal random variable. Okay, that x still, this is what it means. This is going to be the one that results from transforming from the standard normal space to the equivalent original space. But instead of going through the real transformation between the two, I'm going to go through the linearized transformation that I've just defined here. So assuming that we have that linearized transformation, the mean of that equivalent normalized original space is going to be x star minus the Jacobian of x with respect to u times u star. And the covariance matrix in my equivalent normal space is going to be simply the Jacobian inverse times my identity matrix times the transpose of that inverse Jacobian. So basically that boils down to simply the Jacobian of x with respect to u, and the same thing transpose. So by simply multiplying these two Jacobian, I'm going to have my equivalent covariance matrix, and I'm going to be able to use its decomposition to obtain a sensitivity matrix. And what happened when we do this? So here, if we look at the transformation between the standard normal space on the left and the original space in blue on the right. So in that case, we obtain the transformation between the standard normal and the original space by using the equality of the CDF. So if we look at both plane line here, so if I want to go from this 0.89 coordinate, I'm going to read what is its value in the standard normal space, not in the CDF. CDF inverse, I'm going to get 0. Okay, so this is the typical transformation we would get if we have standard normal space and the original space. Now what we want to do, if we plot the same relation here in a 3D graph, we have here our standard normal CDF, we have our original CDF in blue, and the relationship between these two through the equality of the CDF gives me this nonlinear relationship. So what we're going to do is that we're going to linearize that transformation at the design point here. And then if we go from the original space to the standard normal space to the original space, we're going to get the curve in purple here, which is going to be my equivalent Gaussian in the original space, which is going to give me this dashed line here, which is going to be the equivalent normal for my original space. And this is what I'm going to use to define my sensitivity analysis. So if we go back to our reformulated limit state function, and now I'm going to replace into u that transformation through the linearized function. So u is going to be equal to u star plus the Jacobian of u with respect to x times x tilde minus x star. So here, beta minus alpha u, by definition, it's equal to 0. So I'm only going to have what I have on the right-hand side, which is minus alpha hat, the Jacobian times x tilde minus x star. So the expected value of what I have here is going to be equal to the function I have evaluated at its mean. So I'm simply going to have this. And if we expand the mean being what we saw on the previous slide, which is x star minus the Jacobian times u star. So I have here x star minus x star. So this goes away. I only have alpha times the Jacobian times the inverse of the Jacobian times u star. So in this case, the Jacobian times its inverse is going to be equal to the identity matrix. I have alpha times u star. Alpha times u star is simply beta. Okay, so I go back on my feet. I have the same thing as I'm supposed to obtain. Now, if we look at the variance of this is what we used previously in order to quantify the relative importance of each of our random variables. So in that case, I'm going to have, if I apply it to the same thing here, I'm going to have alpha, Jacobian, the covariance matrix, and the same thing transpose. So in this case, what I'm going to do is I'm going to break down this covariance matrix into two terms. The first term is going to be simply the variance terms, and the second one is going to be the full covariance matrix minus the covariance terms or the variance terms I have here. So this is going to quantify the relative importance of the covariance into the normalized safety margin. What I have here is going to quantify the relative importance of each of the variance of the variable into that normalized safety margin. This is what we're going to use to build our gamma importance metric. So a gamma hat is going to be defined by this alpha, the negative gradient vector, normalized gradient vector, times the Jacobian of u to x, and the standard deviation matrix for my standard standard equivalent space. Divide by the norm of this vector, where each gamma I corresponds to the relative importance of my xi with respect to the normalized safety margin. So again, this is the same interpretation as my alpha square, meaning that a negative value means that the variable contributes to capacity, positive, it contributes to the demand, and we can interpret the relative sign of my gamma hat as the relative importance of my random variables. So if we review the same problem exactly, now we're going to use a Natat distribution to model the joint probability density, because now we have a case with dependency. We cannot directly use the alpha square as sensitivity metric. Now what we're going to do, we're going to build our equivalent covariance in our x delta space by multiplying the two Jacobian of the transformation from u to x. And we're going to look at what is our standard deviation matrix, which is going to be the diagonal terms of my covariance matrix. So we're going to take the square root of them. So we build our joint probability density using an Natat distribution. So we build our correlation matrix by looking at what is going to be our correlation coefficient in the correlated standard normal space. So we're going to obtain 0.31. So it's going to be 0.30 times that correction coefficient. We can take its Cholesky decomposition to have L0. And this is going to be my Jacobian. So we're going to have that inverse of L0 times a diagonal matrix of the ratio between the PDF in the original space and the PDF in the standard normal space for each of my variables. So when we use Natat, we need to go from the original space x1, x2 to a correlated standard normal space z1, z2 to the uncorrelated standard normal space. And going from this to this, so from x to z is going to be through the equality of the CDF. From z to u, I need to multiply by the inverse of the Cholesky decomposition. From u to z, I multiply by this same inverse of the Cholesky decomposition. So in this case, L0 times u. And from z to x, it's to the reverse of these CDF equalities. So here, what we're going to get as a problem is our alpha app is going to be minus 0.69 and 0.63. So in that case, that could have led us to think that the second variable is slightly more important than the first one. So the solicitation is slightly more, but when we consider that alpha hat, we see that these signs are reversed. So the signs are still the same, but the magnitudes are reversed, meaning that the first variable, the dimension, is slightly more important than the solicitation. So we can directly, using the quantity we've already obtained from a form analysis, obtain this gamma vector that's going to give us the relative importance of each of our variable. Now let's look at how can we use these concepts in order to calibrate the coefficients that we have in our design codes. So what is the origin of these design codes? How can we compute them? And how can we look at an apply example on how are these factors determined? So typically in design codes, we have expressions such as this. So we're going to have coefficients here that are going to weight down the variable associated with the capacity and weight up the variable associated with demand. So why did we use such approach is that before introducing those coefficients, when we were using some safety factor where we're going to have admissible stress, we're going to say that for different structure, in this case, bridges having different spans, many of them would have vastly different reliability index corresponding to vastly different failure probabilities. Whereas after the introduction of the load resistant factor design, where we introduce those coefficients, here for different bridges, in this case having different span, we would all have roughly the same reliability index, that same beta. And this is what we want, so that at the scale of network of infrastructure, we want to have the same risk or the same exposure to failure across all of our structure, which wasn't possible before by only using a safety factor on the admissible stress. So the goal is to calibrate these values, so all these coefficients, in order to obtain the same reliability index across a population of structure. So how do we do this? So first, we're going to make the hypothesis that our nominal design value x bar is equal to the mean that we're always considering, okay, the mean of our random variables. So then, by definition, the coefficients phi I associated with one random variable should be equal to the value of that variable at the design point divided by its mean value. So it's like, in this case, we can see that for the first variable, so if we do that phi1 times the mean of x1 or its nominal value, that's going to bring me to the design point. Same thing for phi2 x2, it's going to bring me for the second component to the design point. And the design point is where we're actually designing our new structure, because we see that if we don't satisfy the equation, such as this one, we're going to say that our design is not admissible. If it's satisfied, it's going to be admissible. So it's like if we would be designing on that limit state surface, okay? And we want with dose factor to take us away from that limit state surface, okay? And in that case, there's a one-to-one correspondence between the X star and the U star. So the design point in the original space and the design point in standard normal space, where in the normal space, or standard normal space, the length of U star is equal to beta, my reliability index. So what happened if, when I'm analyzing these quantities, for some structures I'm analyzing, the beta is not exactly what is specified or what do I want in the code. So in that case, I need to adjust my analysis. I need to shift away my mean from where it is currently by a factor delta. And that delta, I want it to be the argument that is the minimum, such that the delta will allow me to satisfy that the beta I'm computing is equal to the beta that is specified in the code. And to do this, I'm going to simply move away my mean in the same direction as defined by alpha, and I'm going to move it by a quantity that is proportional, this is my lambda factor, to the difference between the beta specified in the code and the current beta that I'm computing here. And to do this, I'm going to repeat exactly the same step that I have in my IHLRF methods that I've seen already in module 6. So in module 6, we had the step here 5, 6, 7. So I do every step from 1 to 6 being the same. And here, before recomputing my new corresponding point in the original space, I'm going to do that additional step. So in this case, I'm going to do my new mean is the current mean minus the difference between the specified beta and the one I'm computing times lambda times alpha, lambda alpha being my negative gradient normalized vector. And then I simply go up to the second step to find my U star. And by doing this, I'm going to be able to compute what is going to be my safety factor by taking the ratio while matching a specified beta. So if we look at this through the same example that we've seen before, so we have two variables, the dimension of my bar, we have the solicitation, we have a joint distribution with some correlation. And the question that we want to answer is what should have been the, the factors phi d and phi s that should weight down the dimension, weight up the solicitation, if we want to meet first a target reliability of 1.67. This is the reliability that we've or the reliability index we have already obtained from this problem. So in that case, if we look at the beta we obtained from this problem, 1.67, this is what we already got in the previous module. The x star corresponding to the design point in the original space, 7.82, 18.34 for my second variable. So if I divide that x star divide by my original mean, I'm going to get as coefficients 0.78 for my dimension. So I effectively weighted down, and 1.22 for my solution. I effectively weighted up. Okay, perfect. So this is a case where we had a target beta of 1.60 something. In this case, what happened if our target beta is 3? We need to use that correction procedure in the IHLRF algorithm to move away our mean. So in that case, the original mean was here at x0, and gradually through that IHLRF algorithm, I move it away to this point. So now I'm going to satisfy my problem of having a beta equal 3, and this is my new x star. So now my mean plus the correction I've applied delta x is this new corrected mean. And now my coefficients are 0.76 and 1.79. So these are the coefficient I would apply on both my dimension and solicitation. Perfect. So now we're going to look at the third example where now we have no correlation, but we're going to heavily modify the standard deviation associated with the solicitation, making it a lot less uncertain. And we're going to see that's going to modify our joint probability density. And we still want to satisfy a target of beta equal 3. So now we can see the contour of my joint PDF. The first variable associated with dimension is much dominant over the second the dimension, which is going to be the solicitation. So in that case, the resulting correction factor that I have, phi, are 0.62 for my dimension. The one is represented by the horizontal one here, and 1.09 for the solicitation. So the force applied on my bar. So you can see that in this case, it's really the variability in my horizontal axis that governs the problem. And automatically that coefficient has been really weighted down for the dimension, whereas it's really close to 1 for the solicitation. So it really inherently reflects the uncertainty I have about all of my variable in my problem. In this case, dimension is a lot more uncertain than solicitation. So it's really the one that's going to be driving my uncertainty in my reliability index. So that's why I have a higher correction on the dimension than on the solicitation. And that procedure is going to automatically tell you which variable should be weighted by what quantity in order to satisfy your reliability index specified in the code. That's it for the code calibration. Now we're going to look at how can we quantify the relative importance of not each of the random variables themselves, but the parameter involved in defining the joint distribution for your random variable. So we're going to look at how can we estimate the gradient of beta with respect to all the variable involved into our joint probability density function. We're going to look at how can we compute the Jacobian for that same quantity in the transformation function from the original space to the parameters, and we're going to look at an example application. So sorry, I skipped some slides. So first, what we want to do is we want to compute these two gradient vector. So if we have x, a vector of n dimension involving random variable that could be used into the resistance or loading model. So f of x is going to be our joint probability density, which implicitly depends upon theta, theta being the parameter of that joint probability density, which could involve all the parameters involved in my marginal distribution for those variables. And what we were looking to quantify is what is that gradient vector. So the derivative of beta with respect to each of the parameter in that theta f. So we can look for the gradient of beta with respect to those parameter, or pf with respect to those parameters. So in order to express that gradient vector, we need to look at this formulation. First, we know that our design point u star, we can make it explicitly function of the parameter theta we just expressed that are involved in the joint probability density of each of my random variable. So in that case, this is obtained by the product of beta, which we could make explicitly function of theta, and alpha hat of theta, where also we have that uh, alpha times alpha transpose is equal to 1. So if I project the negative gradient vector, normalized gradient vector on itself, is going to, since it's a unit-led vector, is going to give me the scalar 1. And I'm going to use this to say, okay, I want to take the derivative of that alpha alpha transpose, because I know derivative of a constant should be 0. So if I take the derivative of this with respect to 0, the simple rule of derivation will give me this formulation. Derivative of alpha with respect to theta times alpha transpose, alpha times derivative of alpha. Perfect. And now that gives me 2 times alpha times derivative of alpha with respect to theta will give me 0. And now if I look at what I have on the left-hand side, the derivative of u star with respect to theta is going to give me using the same derivative rule, derivative of beta with respect to theta times alpha plus beta times derivative of alpha times d theta. So in that case, if we look at what we already had here, so I'm going to have alpha times alpha transpose. It's going to give me 1. And we're going to have here, derivative of alpha times alpha must be equal to 0. So that's going to simplify everything to the derivative of beta with respect to theta, this is what I'm looking for, must be equal to alpha times the derivative of my design point with respect to theta, So only thing I need to find is what is that derivative of the design point with respect to my parameters. And how do I obtain this? It's simply by taking the partial derivative of my transformation function. So going from x to u, I also depend on the parameter theta associated with my marginal PDFs. So what I can do is I can do the same thing, but evaluate that for u star or for x star. So in that case, the derivative of my beta with respect to each parameter, which is that gradient vector I'm looking for, is going to be alpha times the Jacobian from of u with respect to my theta. And this is going to be evaluated at x star. So in this case, that Jacobian of my u space with respect to my theta is going to be equal in that first term. Here is the derivative of my transformation evaluated at x star for u1 with respect to theta 1. Okay, and I can do this for all my quantities, for all my variable, for all my parameter theta. Then this will give me the sensitivity of beta with respect to my parameter. What if I want the derivative of my probability of failure with respect to those parameters? I need to multiply the gradient vector I will have obtained here by the derivative of the transformation from pf to theta. Remember, this is the CDF of minus beta. The derivative of the CDF is going to give me minus the PDF of beta. So just by multiplying these quantities, I'm now going to have the sensitivity of PF with respect to those same theta. And the nice thing is that for a NetApp joint probability density function, that Jacobian from the U space with respect to the parameter theta, so the derivative of the transformation, is going to be equal to simply the product of the inverse of the Cholesky decomposition of my correlation matrix in the correlated standard normal space times these ratio. So I'm going to have 1 divided by the PDF standard normal PDF of my Z star. So the Z values evaluated at the design point times the ratio between the derivative of my, or simply not the ratio, but simply the derivative of my CDF of the current variable I'm looking at divided by my the derivative of my CDF with respect to the parameter I'm looking for. And for all other variables, they're evaluated at their design points. And here, all those derivatives can be easily evaluated using numerical differentiation. So if I want to approximate this derivative, what I'm going to do is I'm going to evaluate my CDF for the variable I'm looking at, where I'm going to perturb the parameters by a quantity delta J. Delta theta j, sorry, minus the CDF evaluated at the nominal value for delta. And I'm going to divide by that perturbation I add. And in practice, I'm going to use these perturbations that are infinitely small. So in that case, that's going to allow me to compute all that these derivatives I want to obtain. So if we go back and revisit our same example that we've seen in module 6 at example 6.4, now I want to compute the sensitivity of my beta that I compute with respect to those four parameters. So the mean for my log normal, the standard deviation for my log normal, the mean of the log of my this is going to be equivalent to the lambda zeta for my log normal random variable, mu s and beta s. These are the two parameters for my Gumbel distribution. So I want to take the gradient of beta with respect to those four parameters. So I have my transformation function from z to u. I have a transformation from z to x. I have my Jacobian. This is the classic formulation for the net dot distribution. And that's going to allow me to compute that Jacobian matrix. Okay, the Jacobian of the transformation function with respect to all of the parameters involved in the marginal PDF. So here I have two variables, u1, u2 represented in two line, and I have four parameters, so I'm going to have four columns. So only parameters 1 and 2 involved in U1, parameter 3 and 4 involved in U2. So I have those four terms that I need to compute. So after computing these Jacobian terms, I'm going to get these numerical results. So these are the first two parameters associated with the log normal, the third and fourth parameter associated with the Gumbel. So what is the interpretation? If I change lambda for my log normal random variable by 1 unit, the change in beta is going to be 4.7. If I change of 1 unit zeta, I'm going to get a change in minus 5.4 for beta. So, and we have the same thing for the other parameters. So this is fairly hard to interpret because I don't really have a physical representation of what is lambda, zeta, mu, and beta in this case. But we have the same thing for probability of failure, so same relative effect for PF, but these are fairly hard to interpret because it's hard to attach a meaning to those PDF or the parameter of those PDF for cases other than the normal where we directly have the mean and variance. So what we want to do is to reparameterize all of this in order to obtain the sensitivity with respect to m of x and my standard deviation. So to do this, we're going to see how can we make the transformation to obtain the sensitivity explicitly with respect to the mean and standard deviation, and how can we normalize the sensitivity metric in order to have something that is even more interpretable. So as I said, except for the normal that are parameterized by a mean vector and a standard deviation, all the other variables are, the parameters are very hard to interpret. So then how can we modify our parameterization so that we can have the sensitivity, so the gradient vector of beta with respect to these coordinates? So the key is we need to define what are the functions that allow us to go from these native parameter theta f to the mean and standard deviation. And actually, when we saw in module 3, we already defined all of these functions. We already have closed form solution for all of those. So then the only thing we need to do is with respect to the chain rule of derivation, we can just multiply the gradient we've obtained previously times the Jacobian of these transformation function. And that's going to automatically give me the sensitivity, not with respect to those original parameter theta f, but with respect to the mean and standard deviation. This is what I'm looking for. So to obtain those sensitivity of beta with respect to mean, I'm going to simply take the gradient I had before with respect to the parameter times the partial derivative of those native parameter with respect to the mean. I'm going to do the same thing with respect to the standard deviation. And then we can also make them adimensional. So remove the kind of scaling effect by multiplying by dx, the standard deviation matrix, or in this case, the vector of standard deviation, associated with each of my variables. So if we look at delta, this is going to be our adimensional sensitivity metric. It's going to be equal to the derivative of beta with respect to the mean times the standard deviation. And we're going to do this for each of our dimensions. So what is its interpretation of that delta vector? Is that if I move my mean by one standard deviation, how much does it affect my beta? Okay, and this is going to be the most interpretable component. We're going to have the same thing for the standard deviation. So this is going to be eta. So eta tells me if I move my standard deviation by one standard deviation, by how much my beta moves. So it's going to be much easier to directly interpret these delta and eta than the gradient vector we had previously. So now if we use these new concept to evaluate the sensitivity with respect to mean and variance, and also with respect to my n-dimensional quantities delta and eta. So we have here the transformation function we saw in module 3 for our log normal random variable, this is x1, and for our Gumbel random variable, this is x2. So we have here the transformation function with respect from the lambda and zeta to my original mean and here coefficient of variation. And we have the mu and beta, the native parameter of my Gumbel, that are a function of the mean of x2 and the standard deviation of x2. So in that case, we are going to build that Jacobian matrix. We have here 4 parameters, which correspond to my, the 4 parameters correspond in this case to my 4 lines. So we're going to have mu, we're going to have lambda, we're going to have zeta, we're going to have mu, and we're going to have beta. And my 4 column will correspond to my 4 moment, mu of x1, mu of x2, sigma of x1, sigma of x2. Okay, so these are my 4 lines, these are my 4 columns. And I want to compute the partial derivative of all of these with respect to all of those. So if I look at this, which one is involved in those functions, I'm going to get this very sparse matrix, but I compute all the coefficients. In that case, I can compute all of them analytically. So if I evaluate these results numerically, if I want a gradient of beta with respect to mean and standard deviation, I'm going to get these terms, meaning that if I change the mean by 1 unit, this is by how much it's going to change my beta. If I change my standard deviation for first variable by 1 unit, this is by how much it's going to change my beta. So what you can see is that the first variable, so we're going to have in order mu s, mu d, mu s, sigma d, sigma s. So d is associated with the resistance. So we see that if we change mu d, so it's going to change by increasing my reliability index, which would I would imagine intuitively. If I increase the solicitation, it's going to decrease my beta. It's going to make my failure more probable. This also corresponds to what I expect. And you can see that in both cases, if I increase the standard deviation of either variable associated with solicitation and resistance, both are going to decrease my reliability index, making my failure more probable. Okay, so moving the mean depends on whether it is associated with solicitation or demand. Moving the standard deviation, the amount of uncertainty in my problem, is in most cases going to reduce my reliability index. If we do the same thing for obtaining that sensitivity with respect not to beta, my reliability index, but my probability of failure, I simply modify by minus my standard normal PDF of minus beta. So this is going to give me the same thing, but now it's the sensitivity with respect to probability of failure with respect to those moments rather than being beta, but we have the same interpretation. If we look at our high-dimensional quantities now, we're going to have here for delta 1.2 and minus 0.64. So what does it mean? So in this case, if I move my mean by 1 standard deviation, I'm going to increase my beta by 1.2. If I move my mean for solicitation by 1 standard deviation, I'm going to decrease by 0.64 my reliability index. My eta is the same thing, but for the standard deviation. If I move my standard deviation for my dimension by one standard deviation, sorry, I'm going to decrease my reliability index by 1.2, same thing, minus 0.43. If I move my standard deviation for my solicitation by 1 standard deviation, this is about how much I'm going to decrease my reliability index. And we can use these sensitivity metrics to guide us into upon which variable and which parameter should we act upon in the case where our analysis don't allow us to satisfy the code requirements. So if we look at the summary of what we've seen in this module, we first look at the importance measure of each of my individual random variable into my normalized safety margin. And we can set it in a case where we have independent random variable. The alpha square was directly guiding us into which variable is more important. In the case where we have dependency, we need to look at that modified gamma hat sensitivity measure. So that's going to give us that ratio here, the relative importance of each variable into my normalized safety margin. And we can interpret the sign of this quantity, meaning if it's negative, it's going to contribute to capacity, positive, going to contribute to the demand. Then we can look at the importance of each of my individual parameter as involved in my marginal PDF into either PF or beta. So in that case, we can do this by looking at the gradient of beta with respect to all of my parameters. So this is going to be defined by alpha hat times the Jacobian of the transformation with respect to my parameter theta. We saw that this is not very interpretable. So we then decide to make the sensitivity not with respect to the original parameter theta, but with respect to the mean and standard deviation. So we obtain this by simply multiplying the gradient we have here by the Jacobian of the transformation. This case, not between x and u, but between theta f and the mean and standard deviation. These transformation functions we've already saw in module, not 3, in module 2, where we saw each of the individual probability distribution function. Then we saw for the calibration of codes that the calibration factor we're using in code is actually the ratio between the design point for each of my variable divided by their nominal value, which is in this case taken as their mean. And finally, the sensitivity metrics we're going to use in order to guide us into upon which variable should we act in the case where we don't satisfy our reliability index after doing a reliability analysis. We're going to guide our action with respect to the delta and eta, which are my adimensional sensitivity metrics that tells me if I move my mean by 1 standard deviation, by how much I move my beta. If I move my standard deviation by 1 standard deviation, by how much I move my beta. These are my two delta and eta sensitivity measure. And these are the tools that I'm going to use in order to say if at the outcome of my reliability analysis, my beta that I compute don't satisfy the requirement of the code, which variable should I act upon by how much if I want a beta that's going to satisfy my that's going to satisfy my codes. And in this case, these action could be either reinforcement that will play, say, on the mean value of some of the variables, or they could be some information gathering actions, such as measuring some quantities in the field in order to reduce the uncertainty associated with some of the variables. So that concludes what we saw here in module 7. The next one is going to be a jump back into an analytical estimation function where we're going to see the SORM method, second order reliability method, in order to overcome some of the limitation of form by replacing the linearized function that we use to model the limit state function by a parabola, a quadratic limit state function that's going to decrease the approximation error we can commit by approximating these quantities.